Hello and welcome to this introductory tutorial on artificial neural networks. Let's not waste any time. Let's start right at the top and answer that very first question, which is what exactly is an artificial neural network? Well, it is essentially this here, or at least some variation of it. There are many different ways we can manipulate this structure depending on the task at hand. But what we have here on screen is the fundamental way to think about what a simple artificial neural network might look like. We will move on to learning about and applying convolutional neural networks later in this section, but even they really rely on the same foundational architecture, so all of this will apply there as well. Anyway, back to what we see on screen here, and those colored circles that you can see, they are representing things known as neurons, and you can see that they are all linked to each other. And we will get into the different types of neurons and how they connect very soon. But I want to take a step back for a second and discuss why this structure was created in this way. So the reason that an artificial neural network is called artificial, and the reason why it is structured in the way that we see here, was that it was originally designed to essentially mimic the way neurons behave in our own brains. So to generalize, we as humans receive inputs or signals from our senses. These are passed through huge volumes of neurons in our brains, and depending on those inputs and the circumstances, each of those neurons would decide to either fire or not fire, or in other words, decide whether it would pass on some output signal to the next neuron or if it would not. And while this has been a very dodgy biology lesson, this is the underlying logic. This web of neurons are deciding whether or not to pass signals to each other based on the information that they receive. And at the end of all of this, we would have some result, so maybe a decision or an action. Perhaps we see a baseball coming at a certain speed and a certain angle, and we make a decision to swing at it or to leave it. Again, this is all hugely generalized, but the key point is that these artificial neural network models that we'll be learning about and building here in this course are actually loosely modeled off our own brains. And I think that is pretty cool. So let's jump back to our artificial neural network architecture from before, and let's run through at breakneck speed what is going to happen. And before we even do that, let's just set this all up. So we would have some data. Here we're just showing a few observations, but perhaps we have hundreds or thousands or even millions of rows in this table. And we can see in our example here, we have 4 columns. We have 3 features or input variables, and here these are just arbitrarily called x1, x2, and x3. And then we have our output variable that we want to predict over on the right, and this is just called y. And you can see that this is a numeric value, meaning that in this case we are dealing with a regression task. Neural networks can deal with regression tasks as well as binary classification and multi-class classification tasks. But for now, let's just use this regression example. So let's do this. Step 1. From our data, the feature values from the first row or observation, so 0.51 for x1, 0.97 for x2, and 0.66 for x3, enter the network here in what is known as the input layer. Each one of these blue circles in our input layer would be used to represent the data from each one of those features or input variables. So you can see that top one is for x1, the middle is for x2, and the bottom one for x3. If we had 10 features, there would be 10 of these neurons in our input layer. If we had 500 features in our data, we would have 500 neurons in the input layer, and so on. There would be an input neuron for each feature or input variable in our dataset. From there, these values are passed through to the middle section of our network. The columns of yellow circles that we can see here are known as hidden layers, and each of these is made up of some number of neurons as well. Now, purely because it was easy to draw, both hidden layers here have 4 neurons. So counting down from the top to the bottom of each yellow column, we have 4 neurons. Now you might have noticed that the neurons in our input layer are connected to all of the neurons in our first hidden layer. And you can see that all of the neurons in that first hidden layer are connected to all of the neurons in the second hidden layer. And these connections between neurons is how information is passed from left to right through our network in a process known as forward propagation. So in other words, we are moving the values from our data forward through the network. So let's take a closer look at this process. Just like we saw with the emoji example of our brain's neurons, each of these neurons in the hidden layers takes in values, or what we could call signals or information, from the neurons in the preceding layer. And then, based on some clever mathematical logic involving weight values, which we'll talk about more later, but these essentially dictate how important the information that is being passed on is deemed to be, the receiving neuron decides what information or value it should pass on to the neurons in the following layer. And while I am essentially just highlighting, or at least focusing on, a portion of the network here, it's important to note that every connection and neuron in the network will essentially follow the same process. And these decisions that the neurons are making around what to pass on to the subsequent neurons, or in other words, whether or not that neuron should be fired or activated, are based on another bit of mathematical logic called an activation function. Now, what I've covered in the last 3 slides in terms of weight values and activation functions is really the engine of neural networks. It is what makes them work the way that they do. And because these concepts are super important to understand, we will be covering them both off in much more detail in the next 2 tutorials. But for now, let me just say one more thing about these weight values. Like I mentioned, these are essentially what dictates how important the information being passed on is for predicting whatever it is we're looking to predict. To start with, the network has no clue as to this importance, so the weight values will most often just start off being random numbers between 0 and 1. But over time, they will be cleverly adjusted as the importance is understood. And this is exactly what is being referred to when we say that a neural network learns over time, and you'll see how this happens very soon. Now, moving back to our full diagram of the hidden layers, it's worth noting that the number of hidden layers that we have in our network and the number of neurons within each of these hidden layers can be set by the data scientist depending on the task. And at a really high level, this often just takes a bit of trial and error to see what works best. There aren't any strict rules that explicitly tell us how many of either we should have. The more hidden layers there are, or here in the image, the more yellow columns of neurons, the deeper the network is considered to be. And the more neurons we have in our hidden layers, the wider our network is considered to be, which all seems a bit counterintuitive based on how we visualize neural networks. Anyway, like I alluded to earlier, these hidden layers are where all of the cleverness of neural networks come into play. The way that data is passed onward through these with the weightings on each connection and then an activation function is the reason why we can solve very abstract problems such as language translation or identifying what is in an image, things that classic machine learning algorithms often struggle to do. Now back to our neural network architecture that we see on screen here, and since in our example we're working with a regression task, in other words, we want our output to be a single value rather than a probability of belonging to a certain class, the final part of our network, or essentially the result that we spoke about when discussing our brains earlier, would simply have one neuron, which will be the value for each prediction. And this last layer of the network is aptly just known as the output layer. The passing of information from the final hidden layer to our output layer is step 3 of the process. Now, as a quick aside, if we were dealing with a classification problem instead, so for example, we wanted to predict whether, based on some information at hand, a poker player was going to fold, check, or call, then we might have multiple neurons in the output layer, one for each possible class or outcome. And in most cases, we would want those neurons to represent the probability of each data point belonging to each of those classes. For now, however, let's just stick with our current regression example and continue working through the high-level process. And at this stage, I know this is a lot to take in, especially if this is your first time learning about neural networks. So let's very quickly just refresh the steps so far. So step 1, the feature values from the first row or observation in our data enter the network here in what is known as the input layer. From there, these values are passed to and through our hidden layers with weighting values on each connection determining the importance of the information and activation functions on each receiving neuron determining what is passed on to the subsequent layers and ultimately the output layer where we get our prediction. And until now, we've just represented that prediction with the y-hat symbol that you can see in the green circle. But let's actually replace that with a hypothetical prediction value. So let's say the network predicted the output value to be 0.28, which you can now see in the green circle over on the right of screen. This is our neural network's prediction for that very first observation in our data. And even though we're now using funky neural networks rather than the more classic machine learning techniques, we're still in the realms of supervised learning where we are training the model and we know the correct outputs for the training data. So let's head back and check the actual output value. And as we can see, our prediction of 0.28 is quite a bit lower than the actual value of 0.77. To be honest, we shouldn't be surprised that there's a bit of a mismatch. On the very first pass through, the network's just assigned random weighting values on the connections, and therefore we can't expect anything apart from a random prediction. But now the neural network has a chance to learn. And how it does all of this learning is very, very cool. It will essentially ask itself, how wrong was I? What was the mismatch between my prediction for the output and the actual value for the output? And this mismatch is often known as the cost or the loss. And this calculation is step 4 of our process. Once the network knows how wrong it was, it will look at ways to reduce that loss, or in other words, increase the accuracy of its prediction or predictions. But how exactly does it do that? Well, there is essentially one important part of our network that can be changed or updated, and in doing so would have a direct effect on the prediction value. I am talking about the weighting values on each of our connections. And you can see those connections as dotted red lines here on screen. And remember, each one of those connections has an independent weighting value associated with it. In a process called back propagation, we essentially head back through the network from right to left. And using a couple of clever mathematical processes called the chain rule and gradient descent, small changes are iteratively made to each of the weight values until we get a set of values that results in that mismatch between prediction and actual being either 0 or some value very close to 0. To make this back propagation process just a little bit clearer, and don't worry, we will go into much more depth on all of this in later tutorials, including those terms I just used, so the chain rule and gradient descent. Let's visualize what is happening at this stage. To reiterate where we are at here, we've started with randomly assigned weighting values, and those have provided a prediction of 0.28 for this single data point. The network compared that to the actual output value of 0.77 and said, yep, those weight values aren't quite right, so let's nudge them around a bit. So the gradient descent process kicks in and we make our first update to the weights, or in other words, we alter their values. And after these alterations have been made, we get a new prediction for this particular observation or data point of 0.45. So this is closer to our actual output value of 0.77, but gradient descent isn't satisfied, so it updates the weights again. And this time we get a prediction of 0.61. Better, but let's keep going. We make another update, resulting in a prediction of 0.71. We are close now. We update the weights again, and this time we get a prediction of 0.77. So an error or loss or mismatch of 0. Gradient descent has done it. It has figured out which combination of weight values results in an optimal or near optimal prediction, one that minimizes our error or our loss. And this is fantastic. But let's remember one thing. All of this was only for our very first data point, so we're not finished yet. We have a set of weight values now that are most likely better than the randomly assigned ones that we started with. So the network goes back to the data and grabs the next observation, and the process continues. The input values for this second observation enter the network here in the input layer, exactly like we saw last time. And from there, these values are passed to and then through our hidden layers, starting with the weighting values we got to last time on each connection, and activation functions on each receiving neuron, determining what is passed on to the subsequent layers, and ultimately the output layer where we get our predicted value for this observation. The prediction, just like we saw last time, is then compared to the actual output value, and the loss is again calculated based upon how much of a mismatch there is. Once we know the scale of this mismatch, the backpropagation process kicks in, where our friend gradient descent again maneuvers and updates the weights until we get an optimal or near optimal set of values that again brings our error or loss down as far as possible. And the network will continue this process for all the observations in our dataset, continually evolving and refining its view of the best weight values across all of our data. The process of the network getting through all of the observations in our dataset is known as an epoch, and this is a term that you will come across a lot when building deep learning models. As you'll see, when we're in Python coding up our very own artificial neural network, we will specify the number of epochs that we want to take place during the training process, or in other words, the number of times we want to run through all of our data, updating and refining the weight values. And after all of these refinements, hopefully we end up at a point where the network has discovered through its intricate web of neurons and weights a really accurate mapping that links our input values to our output values, which we could then use to predict on new unseen data. Now, before we finish up this super high level overview of artificial neural networks, I want to make one quite important side note on this whole process that I've outlined here. While we discussed a scenario where the weights of the network were adjusted after each individual observation was run forwards through the network, this isn't always the case. Updating the weights after each individual observation is passed through, like we've done here, means we're applying something known as stochastic gradient descent, or SGD for short. In this scenario, we are basing our weight adjustment decisions on the mismatch between the predicted output and the actual output for only that single observation, and the weight values we end up with after those adjustments go on to be the starting weight values for the next observation. Sometimes you'll see scenarios where the weights in the network aren't updated until all the observations have flowed forwards through the network, and in this case we'll often be using the mean or average mismatch between predicted outputs and actual outputs to determine the adjustments that should be made to the weights at that point. This approach is commonly referred to as batch gradient descent. Now, what you will more often see in practice is actually a mixture of the two, where we update weights after a subset of observations have flowed through. And this works just the same as batch gradient descent, in that we often take the mean mismatch between the predictions and the actuals for that subset. This approach, as you will see in the practical tutorials, is known as mini batch gradient descent. So as an example, if we had 1,000 observations in total in our training set, and we set a mini batch size of 50, our weights would be updated 20 times per epoch. So 50 of our observations would pass forwards through the network. The loss would be calculated for each of them. The average loss would be calculated over those 50, and the weight adjustments would be based upon that loss. There are pros and cons to each of these approaches, and these range from quite simple to quite complex, but no need to worry about them too much right now. It is just useful to know as we get nearer to coding up our very own artificial neural network in Python, as we will be setting something called a batch size prior to training, and it's good to know exactly what that means. But with that, I am happy to say that you now know pretty much everything you need to know about how an artificial neural network does what it does. Of course, we will be diving much deeper into all of the finer details as we progress, but this is a really, really good start, so well done. In the next tutorial, we are going to be learning a little bit more about these weight values that dictate the importance of the information flowing through the network. This is a fundamental part of how neural networks do what they do, so it's really important to understand them in a bit more detail. Like always, I will ensure that we do this as intuitively as possible. I am super excited about this, so I will see you there.